So in the last video, we covered the main principles of the CAN interface. So instead of having master and multiple slaves, we have independent nodes that can share the same data bus. So interesting thing in the CAN interface is that even if we have multiple nodes and having only single bus, we can avoid the data collision. Imagine that node 1 and the node 2 is sending the data at the same time in parallel. In that case, intuitively, we should end up with the data collision. But in the CAN interface, we have really crucial element that we call arbitration that allows us to avoid the data collision. So to understand the arbitration, I need to introduce two technical terms. First, dominant and recessive. So the value of a bit can be either 0 or 1. I guess we can all agree with that. And in the CAN interface, the value is 0, the state 0, we call it dominant. And the state 1, we call it recessive. So instead of using values 0 or 1, we use terms dominant and recessive respectively. And the interesting thing is that if one of the nodes sets the data line to 0, no matter how many other nodes try to set value 1, the final outcome will be 0. So meaning that 0 always wins over 1. For example, if node 1 sets the data line to 0, and if other, let's say, 1,000 nodes set 1, the data line, the outcome, the final state of the line, the data line, would be 0. Okay, so that's why 0 always wins over 1. So that's really crucial to understand it. So let's move on and let's talk about the arbitration process. So the arbitration is a period when multiple nodes fight for the right to control the data line. And eventually, after the arbitration, one of the nodes takes the control of the data line and it can transfer the data. So how does it happen? First, all the nodes convey the message ID, okay, identifier. It's 11-bit, just a number. So during this time, multiple nodes can send data, okay? There's no restriction, okay? So multiple nodes can initiate the data transfer by sending the identifier. But at the same time, when they transfer data, they monitor the data state, the line state. So there's a RX line, so it can constantly read the state of the data line. And if a node transmits 1, but the data line remains 0, what does it mean? It means that there's another node which is sending dominant 0-bit. So it means that this node, the node which was sending value 1, it is out of the game and can stop transmitting because it understands that there is another node which has a message with the higher priority. Okay. So again, let's consider an example. I think after that it will be really clear. So we have node A and node B, and they have messages with the following ID. Okay, with this ID, with these values. And if we consider bit by bit, we have this value and we have this value. So both nodes initiate the data transfer. So both of them will first transmit 0. Nothing is happening in the data line because they have exactly the same bit. So they're reading back, they're getting 0, everything's fine. Next, we have again 0 and 0, nothing is happening. The third bit, this is 0, this is again 0, nothing is happening. And on the first bit, what's happening is that node A will transfer 1, node B will transfer 0, and the output, the state of the data line would be, of course, 0, because 0 always wins over 1. And node A, which is constantly monitoring the data line, will receive 0, and it will understand, wow, and it will understand that, oh, there is another node which is sending the data with the higher priority, so I have to stop. So then what's happening is that node 1 will stop transmitting the message ID. It will stop transmitting, and the node B will keep sending, streaming the message ID followed by the real data. Because of that, multiple nodes can transmit data simultaneously. Okay, there is no any restriction in the number of nodes that can transfer data. But during the arbitration process, bit by bit, the bus resolves and decides which node has data with the highest priority. Okay, so this is how it works. So this way, we can define the priority of the messages and we can avoid the data collision. So if we sum up, so it means that the identifier with the lowest ID has the highest priority, okay? Because with the lowest ID means it has more zeros, more dominant bits, so eventually it will win over other nodes. So that's how it works. And again, we can consider in a simple example. Again, we can take a vehicle. For example, imagine that one of the nodes is sending the data to control the lightning, let's say, level, and there's another node sending data to the braking system. So both nodes can send data simultaneously. There's nothing wrong with that. But as you guess, the data for the braking system, I think, is much higher, has much higher priority than the data to control the lightning. So most probably the message to the braking system should have the ID with the lowest value, so it can win over other nodes. So, but it doesn't mean that we cannot send the data to the lightning. It just needs to wait to other high priority messages to transmit. Then it can take the data line and then transmit the data eventually. So this is how it works.